I know where there's some, right here in the hall, clerk.
No, Molly, not in there. I have enough.
One of these days.
Hi there and welcome back. On this 60B, this Philco 60B chassis, we've got a couple of things to talk about in this video. One is the 4 capacitors that are in this can right here. And what we'll do for part of this video is look at these capacitors and where they are in the circuit and what they're doing and what the risks are if the capacitors fail. So we'll do that first. After that, we'll talk about the power drawn by this circuitry, and we want to talk about it for a couple of reasons. One is that I want to put a fuse in here, and so what value of fuse do we put in? But the second is the B+ voltage. We're developing a very high B+ voltage here, 250 volts or so, and at 117 volts in, it's actually a bit more than that. At 224, 225 volts, which is what I have out of the outlet here, it's considerably more than that, which means that there's extra wear and tear on the tubes and other components. So we'll talk about a couple of ways. Well, first of all, we'll talk about how to calculate what the radio should be drawing, then compare that with what we're getting on the Tipton device. And then secondly, how to reduce that voltage. This may run into 2 videos, I don't know. You know mine, they go on and on and on. Never stop. Anyway, let's talk about capacitors in a can. Let's find these capacitors in a box. Scanning from left to right, the first one is right here, C20B. That capacitor right there. This one is, well, let's talk about what this resistor does. This resistor right here provides bias to the cathode of the 6A7. And there's a DC voltage right here, the top of this resistor, that the current flow through the cathode keeps fairly consistent. But if AC noise gets into here, then it will change this impedance of the resistor and change the biasing on the cathode. So one way to get AC noise out is to put a cathode bypass cap, which is what C20B here is. It runs all AC noise to ground. So DC stays constant right here, AC comes over here, gets shunted to ground, and it keeps the voltage constant on the cathode of the 6A7 tube. So what happens if that fails? If it fails shorted, it will ruin the bias on the cathode. If it fails open, it will also ruin the bias on the cathode because it'll be noisy then. So that one probably should be replaced. The next one we find is C right here. This guy, also a capacitor to ground. And, pardon me, kind of serving the same purpose. We're trying to route any high frequency AC noise on this line right here, this power, which is around 240, 230 volts. To ground. So that capacitor is on a very high voltage line. If this capacitor feels shorted, it will drive that line towards zero and the radio would stop functioning. So that's a good one to replace as well. Oh, right here is one. C20A is right here. Also doing the same thing. This line is providing a bias to this pair of grids right here, suppressor grids, and you want that to stay common so it's shunting all high frequency noise RF noise actually to ground. And finally, and that one should be replaced because if it shorts, it drives this line to ground and the biasing, all of these tubes stop working. So that one should be replaced. And finally, we have one over here. And again, the same issue. These two resistors are providing some biasing for the plate voltage on this 75 tube. And this guy is here to make sure that no noise, no RF noise changes the plate voltage. So that one shorts, plate stops working on the detector tube, and away it goes, the radio stops working. So we have a good reason to replace all four of those capacitors, and we'll do that very thing. By the way, when I talk about AC on here, I'm not really talking about power that comes in the wall. 60 cycles, that's certainly AC, there's no doubt about that. But AC up in this realm, up in here, when you talk about AC up here, you're really talking about high frequencies. Any frequency above DC, above no frequency, above 0 hertz, is AC. And usually when you're talking about things like this bypass cap, this cathode bypass cap, and routing AC to ground, you're really talking about a lot of radio noise that comes in this end, for example, can be introduced into this tube, and this keeps that all calmed down. So AC is not 60 cycles, although it can be in some instances. AC in this discussion actually has to do with radio frequency noise that can get into the radio and cause racket, cause unwanted noise. Because all you want to hear is that really fine talk radio, right? Right. Anyway, thought I'd clear that up. When we talk about power, we're talking about voltage, current, impedance / resistance, and Ohm's law, to be frank. And Ohm's law is something that you need to be aware of if you aren't already, and I'm sure you are. But let's talk about what this radio does under two operating conditions. When it was built in the 1930s, most wall outlets in the United States were at 115 volts AC, give or take. There was some latitude, plus or minus 10%, something like that. At 115 volts, this radio, as it stands today, with a lot of the capacitors replaced, some of the resistors replaced, it draws 500 milliamps, give or take, 0.501 amps to be precise, but it depends on whether it's turned up or turned down, you know, how long it's been running, and so on and so forth. But it's around half an amp. If I turn the variac up and put 124 volts right here at the outlet, which is what my house would deliver to the radio, the current it draws goes up by 53 milliamps, or to 553 milliamps, which doesn't seem like a lot, but it is, because it has ramifications on this side of the power transformer. The voltages go up. When the voltages go up, the tubes work harder, and the whole thing is placed under more stress, including you're stressing the power transformer itself additionally. So what we're after here is to kind of limit the amount of voltage that our power transformer sees so that we can control these voltages and have them be near these high DC voltages for one thing, and the amount of current that flows through our filament string for each of these tubes. How hot do they burn? The hotter they burn, the shorter their lifetime. and they can burn hot enough to be cause distortion as well. So we want to correct that. We want this radio to behave as though it were plugged into a wall in 1936 and was receiving 115 volts AC. So how do we do that? Well, there are a number of ways. So what we want to do is reduce the voltage coming into the primary of our power transformer on the 60B. How do we do that? Well, let's talk about it in terms of what our goals are. What do we want to accomplish? We want to reduce the voltage of the primary from about 124, which is coming out of the wall at my house, to about 115 volts. That's about a 10 volt drop. Now there are any number of, not any number, but a number of ways that that can be done. And let's go through some of them. Some of them are practical, some of them are not practical. Possible but not practical. One is keep the radio plugged into a variac all the time. Not a good idea. The variac is not built for that, first of all. Secondly, you may have you may not have a variac in your living room. This radio is going to my daughter. She's certainly not going to want to have a variac behind the radio that it's plugged into, but it's a possibility. Another is to add a step-down transformer between the outlet and the radio. Again, same issue with the variac. It's another piece of external equipment that will do the job, quite expensively, by the way, will do the job, but is impractical for day-to-day use. Third variation, possibility, is to add a bucking transformer. And I'm interested in this one. We won't do it for this radio, but I'm interested in it because it's how it works is interesting to me. If you're curious about bucking transformers, there's a lot of pretty good information on the internet, and some not so good information, of course. But what a bucking transformer does is it's a small transformer that's connected to the power transformer in the radio, and it makes it, how do I put this? It makes it less efficient. It reduces the efficiency of the transformer by, in essence, not really, but in essence, reducing the number of windings in the transformer, making the output a lower voltage. So it's an interesting idea. It's a fun concept, but again, not one we're going to do for this radio. Another option is to add a dropping resistor to reduce primary input. This is how it's most often done, and that's how we're going to do. We're going to do a variation on this method for this radio, but we just drop a resistor in line with the line coming from the plug-in and use up some energy. Now the way that works is a resistor, well, I'll talk about that more in a minute. That's another version, and we're going to do this one. And finally, you can add a capacitor. Actually, capacitors and AC lines will use up electricity. They have not resistance like a resistor, but they have impedance, and they can reduce the AC or the voltage if it's put in series with one side of the primary, can reduce the AC voltage. It's a not often used. There are a lot of drawbacks. Not often done just with a capacitor, usually with a bunch of other components as well. But it's another option, and one I'll look at maybe with the same time I'll do a video on the bucking transformer. I'll do one on the capacitor voltage reduction method. But not what we're going to do in this radio. We're going to add a dropping resistor. So how and why do we do that? Well, let's look at the schematic. If we zero in here on our power supply, right here, we can cut this line that goes, we have the AC coming in through the plug. We can, and we'll have an on-off switch. And then we can add a fuse in that same line right there. And then we can add a dropping resistor. What's a dropping resistor do? It burns up energy. Resistors burn up energy. They absorb energy and they give it off. They convert that energy into heat, and resistors can get hot. Power resistors get, 10, 20, 100 watts, whatever the need is. But they use up energy by burning up electricity. And so we can calculate what kind of resistor will go right here to make this voltage that would be 124 volts here to 115 thereabouts right here by burning up some energy with a dropping resistor. But since we're in here, we can add one more feature that this radio would like, and that deals with inrush current. When a vacuum tube radio with some smoothing capacitors like this 8 microfarad capacitor across the rectifier right here is turned on, a lot of current rushes in here. It's called inrush for a reason. Rushes in here to charge this capacitor. It also rushes in here to heat up all the filaments on the tube, and it rushes in here to heat up the filament on the 80 rectifier itself, so that the maximum current is flowing through the power transformer into the radio to heat things up and to get capacitors charged. Once that's done, then the amount of current that flows through the transformer is reduced, and it gets down to our nominal 500 milliamps. But as it's charging and heating things up, it's quite a bit more than 500 milliamps. That's called inrush current, and it's hard on the transformer. It's kind of actually hard on the circuits. So if you could limit the amount of current that's going in here, slow it down so that it more slowly heats up the tubes, it more slowly charges the capacitors, that might be a good thing to do. And the way you can do that is by adding a thermistor in series with the dropping resistor, and in this case the fuse. And we'll talk about thermistors as we go through this video. But for right now, that's what we're going to do. We're going to add a dropping resistor and we're going to add a thermistor, and we need to talk about how to calculate what combination of components right here are going to get us down to our 115 volts. And we'll do that next. In order to determine what size dropping resistor we're going to need for this Philco, we need a couple of pieces of information. And they're generally readily available if you have the schematic. The schematic usually has a sheet like this that says, gives you a rundown on what the radio is and how it works. And most often, and sometimes this will be on a paper label as well, particularly for newer radios. But there are two things that we're interested in here. And one is right here. The power consumption is 60 watts. We need to know that to calculate some other stuff. The other piece of data we need is what they presume the wall socket would provide, and that's right here. AC line voltage is 115 volts. So with those two pieces of information, we can calculate how much current is flowing into the radio, how much current the radio requires to operate normally at its expected voltage. So we'll do that next. Let's look at some numbers using Ohm's law. And Ohm's law is one of the most useful tools. Is one of the most useful tools you'll have in your toolbox. And it doesn't hurt to spend a few minutes studying up on it if you haven't before. But fundamentally, it lets us decide if you have all electronics, right, are E for energy, R for resistance, I for current, P for power. Those four things, and you can if you know any two or three of them, you can figure out the other one. So it's a great tool. But what do we know about the Philco radio? We know that it has an expected line voltage of 115 volts. We know that the radio's manufacturer, Philco, said that the power it will consume is 60 watts. So with those two things, we can figure out what the what the current flow into the radio is, because that's what's going to help us decide what size resistor we need. So how do you define current through using Ohm's law? And that's easy. It's current equals power divided by voltage. And Vn is our voltage here. It's 115. So if we use this spreadsheet's massive calculating power, we can divide 60 by 115. And that tells us that this radio operating normally at its 115 volt rating will use 522 milliamps. So we'll just round that up to 522. 522 milliamps. So now we know we can use this number to figure out how much resistance we need to put a dropping resistor in here. So a dropping resistor will drop, in our case, we want to go from 224, 225 volts down to 15 volts. So we'll just say, for sake of argument, that we want to drop 10 volts AC. So the value of the resistor will be R, the formula is E over I. We have a 10 volt line, so we want to have a resistor that will drop 10 volts at 522 milliamps. The value of the resistor will be 19.15 ohms, or 20 ohms. So we'll call it a 20 ohm resistor. So if we put a 20 ohm resistor in line before the transformer, that will drop our 10 volts, and we should have 10 volts or 115 volts going into the primary of the transformer. So that's our goal. That's what we want to do, is find a 20 ohm resistor. How big? Next, we need to figure out what the power rating for our 20 ohm resistor is. And that's another formula from Ohm's law, and we'll use the I squared times R. So we'll take the easy way to do it. We'll take the current 0.522 times 0.522 times our resistor is 20 ohms, and that means we need a 5.5 watt resistor. Now you need to fudge these upwards, so 7 watts, 10 watts wouldn't even hurt, but at least a 5.5 watt resistor valued at 20 ohms should drop 10 ohms if it's plunked down in the middle of our in the line into our power transformer. So there we have it. If we put a dropping resistor in and it has a capacity to dissipate 5.5 watts of power or more, and its value is 20 ohms, we should hit our target 115 volt voltage in to the primary of the power transformer. And that should result in normal wattage output, or output to the rest of the chassis, and nothing should. Now there's one other thing we can do here. We can add another component called a thermistor. A thermistor is a variable resistor in that when it's at room temperature, cold, it has a certain resistance. as it heats up, when the circuit is turned on that it's in, and as it heats up, its resistance drops to a lower value. And that's handy in old equipment like this because it limits the amount of current that can rush into a piece of gear when it's first turned on. Keep in mind that inrush current is higher than standard operating current because it has to do a couple of things. It has to charge capacitors, the electrolytics, and it has to heat everything up, particularly true in tube equipment, not so much true in transistorized equipment, of course. So in tube equipment, everything has to get hot, and then it'll finally operate normally. So when that happens, when you turn on a radio without any kind of current limiting, it consumes maximum current that it can in order to get everything hot as fast as it can and to get its capacitors charged as fast as it can, as fast as they can. So a thermistor, a variable resistor, can limit the amount of current when it's first turned on, and then as the radio warms up and as the thermistor gets hotter, it's the amount of current that it limits goes down, and then the radio can operate normally. It just slows down. It lets the radio ease into being on, if you will. It has a lazy morning, so it doesn't get the shock of being turned on and having everything heating up all at once. A thermistor, did I spell that correctly? I'm not sure. It isn't. It's spelled O-R. A thermistor is available from any parts place. I have a number of on hand. I have a number of CL90 varieties on hand. Let's take a look at the data sheet for a CL90 and see what kind of information we can glean. Here's the data sheet for a CL90 thermistor. This is available on Mouser.com, and they have the components. They're about $2.75 each at this moment, so a very reasonable investment in an old radio. Here are the specs for the CL90 version, the one I have on hand. And the numbers that we need to think about are these right here. First of all is resistance at room temperature. 25C, what is it, mid-70s Fahrenheit. And this CL90 has a resistance of 120 ohms. If we go over here with current flowing through it and it starts to warm up, as it reaches its reasonable 25% dissipation rating, it hits a different resistance value, and that is 7.8 ohms. So at room temperature, with the radio not operating, it'll have 120 ohms. When you turn on the radio, power will start to flow through the thermistor, and this resistance will fairly slowly, there's a time thing that I don't understand, or sorry, don't care about. It's not so slow that you have to wait a day for the radio to start playing normally. It just slows it down. It slows it down by changing the resistance from 120 ohms down to 7.8 ohms if you're not stressing anything. And we don't want to stress anything. So that's our goal. We want to go from 120 ohms at the startup to 7.8 ohms when it's operating normally and the radio is warmed up and you're listening to your favorite music station. So let's see what those two numbers look like when we go back to the spreadsheet and add this CL90 into the circuit. I've added the thermistor cold and operating temperature resistance values to our spreadsheet. Now what we're interested in, we know that putting a 120 ohm resistor in there will greatly reduce the voltage and current going into the primary at start. But as it warms up, it will, and operating normally, it will have 7.8 ohms, give or take. So what we want to do is take this 7.8 ohms and work it back into this value right here, because our dropping resistor no longer is responsible for dropping all 10 volts. Our dropping resistor will now share the burden with the thermistor. The thermistor will drop whatever voltage 7.8 ohms will give us, and the resistor will then only have to drop 20 minus 7.8 ohms. So let me rework this spreadsheet so we can see what's going on. Okay, I've changed this around a little bit, not much. Our goal is the same. We want to drop 10 volts. Our total resistance, the calculation is the same. It's R equals voltage divided by current. In that case, our voltage is 10 volts. Our current is 0.522 amps, which means we need to have a resistance of about 19.16, we'll call it 20 ohms, for sake of argument. So we have a 20 ohm impedance or resistance we need to have in line. Now our thermistor can provide 7.8 when it's at operating temperature, so we'll put that here. 7.8. Little math equals 20 minus 7.8. And that says we need a 12 ohm resistor, 12.2 ohms at 522 milliamps. And that will give us our total of 20 ohms at 522 milliamps. So we need about a 12 ohm resistor. Now let's check its wattage requirement. And that's fairly straightforward as well. Power equals current squared times your resistance. So we can do this 0.522 times 0.522 times the resistance of 12.2. Yes, the wattage in this case is 3.2 watts. So a 5-watt resistor at around 12 ohms would certainly get us in the ballpark. So that's what we're looking for. We're looking for a 12 ohm resistor at 5 watts. Now, do I have a 12 ohm resistor, 5 watts? I kind of doubt it. I'll probably have to order one. But I do have a small collection of power resistors, and maybe I can get close enough. I do know I have a thermistor. So what we're going to do here is add a fuse. We're going to add a resistor at around 12 ohms with a resistor, a wattage of about 5 watts. Should be plenty of headroom. And our thermistor, our CL90 thermistor. And that should bring us down to around our 115 volt desired voltage into our the primary windings of our power transformer. Let's see if it does.